This course is for people interested in learning sciences such as biochemistry in order to scale up into topics such as nutrition and metabolism, medication and drugs, and human physiology, so that they can take control over their health and even apply it into cosmetic treatments like skin injectables and cosmetic devices. Some of this course will be here on YouTube for free as usual. More of it will be on my free school group starting very soon in January 2025. Maybe out already by the time you see this. And the whole thing will be on my paid school group. Like I said, it might have launched already by the time you see this for the first time. So let's start with the basics. 92 naturally occurring elements are what make up all the matter in the world around us. An element is just a single substance that can't be chemically split into anything simpler, like carbon or oxygen or sodium, any of these elements that you've heard of. The first lesson in the course is the basics of atoms, elements, and subatomic particles. We'll start by diving into atomic structure and the nature of isotopes. This understanding is fundamental, not just for chemistry, but also for how biology is linked to the molecular world. Now, elements make up everything around us. They combine to form matter that's made of compounds. A compound is something that's made of multiple different elements. And each element is represented by a symbol, like C for carbon, O for oxygen, Na for sodium, etc., etc. At the core of an element are atoms. And atoms themselves are made up of three tiny particles: protons, neutrons, and electrons. You may have heard some of these before. So let's break down what makes up an atom. At the center, we have the nucleus, which is where the protons and neutrons reside. Protons are positively charged and neutrons are neutral. And electrons, the tiniest of them all, are negatively charged and live outside the nucleus at nearly the speed of light. This is where things get interesting. It's the arrangement of these electrons that determine how an element actually behaves chemically and what it does when it's surrounded by different things. Think of it this way. If you have loads of free hands, you can say hello to loads of people at the same time with loads of handshakes at the same time. If all your hands are full, you can't shake anyone's hand to say hello. Electrons are the hands of atoms. It's how atoms shake each other's hand to see if they can come together and form something new. The atomic number of an element will tell us how many protons are in the nucleus, and the mass number is the combined number of protons and neutrons together. So let's talk about isotopes. Isotopes are atoms of the same element that have different numbers of neutrons in their nuclei. For example, hydrogen has three main isotopes: hydrogen 1, hydrogen 2, which is deuterium, and this is what you're trying to get rid of when you buy deuterium depleted water, and hydrogen 3, which is tritium. They all have one proton, but vary in the number of neutrons. Now, that slight variation in neutrons doesn't change the element, right? It's still hydrogen, but it does change the mass number, or how much it weighs, if you like. Hence why we sometimes use the term heavy water. Hydrogen 1 hasn't got any neutrons. Deuterium has got 1, and tritium has got 2. Some isotopes, like tritium, are radioactive, meaning they aren't stable and they decay over time, releasing radiation. Think of carrying loads of cardboard boxes all over you, but then you decay by dropping a load of them because you're too unstable carrying that many. And eventually, when you've got just 1 or 2 boxes left in your arms, you're stable. You've got grip around them, so you can hold on to those and walk around with no problems. The same goes for carbon, which has isotopes like carbon-12, carbon-13, and carbon-14. These are the isotopes that allow us to work out what our ancestors ate with stable isotope testing so that we can work out what the diet our genes have been selected for is. Each isotope has 6 protons because that's what makes it carbon. But the number of neutrons alongside those protons in the nucleus varies. But what about the electrons? The number of electrons around an atom equals the number of protons in the nucleus. So in a neutral atom, they balance each other out. Positive and negative, same numbers. But here's a twist. Electrons are found in specific regions around the nucleus known as energy levels or shells or orbitals. They don't go zipping around in circles like animations show you. That's just to look nice in an animation. Now, these energy levels are kind of like floors in a building. The lower floors are filled up first. Each level can hold a certain number of electrons, and within these levels, there are sublevels called orbitals, and each orbital can hold up to 2 electrons. And electrons like to fill the lowest energy orbitals first. You can think of energy levels as the drawers of a filing cabinet. And in each drawer, there are folders acting as orbitals to store pieces of paper. Each folder can hold 2 sheets of paper, just like each orbital can hold 2 electrons. So the 2 papers go into a folder, and the folder goes into a drawer. The parallel to this would be 2 electrons go into an orbital, and each orbital exists in an energy level. Let's take a look at, say, hydrogen. This has 1 proton in the nucleus and 1 electron outside. And this electron occupies the first energy level, or the 1s orbital. 1 is the energy level, or the bottom filing cabinet drawer. S is the orbital in that first energy level, or the folder in that bottom drawer. That's the simplest example of electron configuration. And you can summarize that by using orbitals represented as boxes and electrons shown as arrows, which hopefully is on screen now if my editing team, Longwave Digital, has been paying attention. For helium, with 2 protons in the nucleus and 2 electrons outside. Both electrons sit in the 1s orbital. And that's it. This energy level is now full. First one can only hold 2. The bottom drawer's single folder, S folder, can only fit 2 sheets of paper in it. Now, as we move up to more complex elements like lithium or carbon, the electrons start filling higher and higher levels and orbitals within those levels, such as level 2 with 2s and 2p orbitals. Lithium is where it gets a bit more complex. Lithium has 3 electrons. 2 of them fill the 1s orbital, and the third one moves into the 2s orbital, which is the next energy level, or n equals 2. N equals 1 is the first energy level. So S folder in the bottom drawer gets full, they go into the drawer above, use that S folder, then there's a P folder, and then they go into the one above, etc. There's 3 boxes for the 2p orbitals. So each level has 1 of the S kind and 3 of the P kind. Fill the S first, and then start to fill the P. When those are full, too, you then go to the next level up. The 2p orbitals have 2p as in the energy level 2 and the p orbitals there. There's 3 of them. They have 3 shapes known as 2px, 2py, and 2pz, corresponding to the different axes in space. If it was level 3, there'd be 3px, 3py, 3pz, and there's a max of 3 p orbitals in every level after the first, which only has s, which you can see in the diagram, hopefully on screen. And because each p orbital can hold 2 electrons, the total maximum number of electrons held by all p orbitals in each level is 6. By the time we get to the carbon, with its 6 electrons, 2 fill the 1s orbital, 2 fill the 2s, and 2 remaining go into the 2p orbitals in the same level or filing cabinet drawer. It happens in that order too. The 2s orbital gets filled first, and then the electrons move into the 2p orbital. By the time we get to oxygen, which has an atomic number of 8, we filled 1s, 2s, and some of the 2p orbitals. The electrons keep filling these orbitals according to the rules we've mentioned, lowest first and then move up. Now, fluorine has 9 electrons and fills up those 2p orbitals a bit more, And the neon with 10 electrons fills all the 2p orbitals completely. Once they're full, the atoms are stable. This is the reason why neon is so unreactive. It has a full outer shell of electrons. And this stability is from something called the octet rule. Atoms are happiest when their outermost energy level, also known as the valence shell, is full, like you just saw in neon. For most atoms, this means having 8 electrons in the outer shell, 2 in the s orbital and 6 in the p orbitals, like the neon diagram you just saw. This is why atoms react with one another to share or exchange electrons in a way that fills their valence shell, outer shell, and brings them to a more stable state. That's what drives the formation of chemical bonds, like covalent bonds, where atoms share electrons to reach the stable octet configuration. It's why any chemical reaction anywhere takes place, because the electrons in these orbitals want to be in as low an energy state as possible. Neon having a full outer shell is why it doesn't want to share its electrons. It's already full. It's already stable. It doesn't really bond with anything. Helium's full too, right? Its outer shell, valence shell, is 2s, which is full with 2 electrons, and it's therefore very stable. And if you wanted to, you can summarize all of this by using orbitals represented as boxes, like I said, to remind you, and electrons as arrows pointing up and down, opposing, which hopefully will have been on screen somewhere while I've been talking. So let's have a recap of all the information so far before we go any further. So firstly, each element has a unique number of protons in its nucleus, and that's a defining feature of that element. That's what makes it that element. However, the number of neutrons, which are neutral, can vary. And when that happens, we get isotopes. These are different versions of the same element. Same element because it's still got the same number of protons. Second, didn't mean to swear at you there. Isotopes play a pretty important role in biology, such as during stable isotope analysis. They can be stable or unstable, radioactive, and their unique properties make them incredibly useful in research and medicine. Third, electrons are found in atomic orbitals, even though they don't go round in circles like they're orbiting something. Still called orbitals. These orbitals are named things like 1s, 2s, 2p, and so on. P has an X, a Y, and a Z to make 3 in total. And as you move further away from the nucleus, the energy of these orbitals increases. Fourth, when it comes to how electrons fill these orbitals, there's a rule. No more than 2 electrons can occupy any given orbital, whether it's an S or a P or a D or an F. This is known as the Pauli exclusion principle. If you're interested, it states that no 2 fermions can exist in the same quantum state while obeying the laws of quantum mechanics. It may mean nothing to you, but it's the reason we don't fall through the floor into the center of the earth when we're standing around, and why, Botox spreads out from where it's injected through the skin. I'll leave you to Google it if you want to go down a massive, massive rabbit hole. Fifth, if an atom's outermost orbitals are completely full, the atom is considered stable and doesn't easily react with other atoms. These are often elements like noble gases that you find in the far right, I think that's the right of the screen, right column of the periodic table, such as neon, argon, krypton, xenon that you get in car headlights nowadays, etc. Sixth, atoms combine with one another by either sharing electrons in the outer level or losing and gaining them. And this helps them fill their atomic orbitals and achieve a more stable configuration, which is essentially the basis of how chemical bonding works, or the whole of chemistry, if you like. And when you change up the interaction of why this atom interacts with that one, you get compounds. Then the atoms that make up compounds still interact with atoms of other compounds. Then you end up with bigger scale interactions, not just between compounds, but between amino acids, enzymes, water, etc., etc. And you can have things like biology, metabolism, medications, drugs, skincare, LED masks, so on and so on. This is why it's so important to start learning how to take care of your health at such a fundamental level of science, atomic theory. And that's why I'm doing this. I want people to have that ability without relying on a healthcare industry that is sponsored by Big Pharma, let's be honest, and cares, I think, more about lining its own pockets than actually helping people. And this is why I'm going to be starting my own school community soon. It'll start in January 2025. And the whole premise is that it should bring together people that want to improve their health and longevity and look as beautiful as possible while they do it. People that want to look good on the inside as well as the outside. I'll even have videos of things like dermal filler, Botox, laser treatments, etc., all on there. That's why I work in longevity and cosmetic medicine. If the group's already started by the time you see this, hopefully it'll be linked in the description below, as well as my website as well, which is also in the description below. And there's a free group too for those that can't afford anything. I've always put stuff out for free right here on YouTube, and I'll be doing it on school too. I'll be teaching exactly like what you're seeing in this video with educational content, but I'll also be doing live teaching, just like a classroom, and I'm your teacher at the front of the room. But that'll be in the paid group because this is my job at the end of the day. But anyway, enough of the adverts. Apologies. Let's dive deeper into the topic of isotopes. And what we'll do is we'll focus on their specific applications in areas or in sciences like, say, biology and ecology, geology, nutrition, all these sorts of things, because they have a really crucial role there. So isotopes, specifically radioisotopes, are elements with an unstable nucleus that lose mass or energy to achieve a more stable state. Now, this process often results in the emission out of the nucleus of an alpha particle or a beta particle or a gamma ray. Once that decay from the nucleus is complete, a stable element remains. So it's up here, emits something, and then it becomes more stable. If we think about the analogy of someone carrying too many boxes being unstable, they drop boxes or mass to become more stable, and they can carry the remaining boxes very easily. Radioactive isotopes of elements lose mass so they can get back to a comfortable and stable state to carry less boxes, if you like. Now, the use of radioactive isotopes in biology started in the very early 20th century, specifically, I think it was around 1923. Georg Hevesy, if I've said the name right, in the University of Freiburg, measured the distribution of radioactive lead in plants. And he pioneered this method for using isotopes to trace biological processes. You can see where this course is going. His work earned him a Nobel Prize in 1943. I remember reading about it for the first time when I was about 11, I think, but it took me at least like a few weeks to understand what an isotope even was, because I jumped ahead to the more complex stuff, because the simpler things and missed the simpler things that allowed me to actually understand what it was I was reading. Hence why I'm starting with the fundamentals on this course before we move on to much bigger topics, ultimately like human physiology, metabolism, and like medicine in general. But here are the key properties of radioisotopes. Firstly, detection. With specialized equipment, radioisotopes can be detected, allowing scientists to monitor their distribution in organisms and in our environment. Number two, distinctiveness. Radioisotopes of an element are not distinguished from naturally occurring stable isotopes by organisms. So a plant or animal will eat food with carbon-12 as well as carbon-13 or carbon-14 because the electron configuration is still the same, so the bonding in behavior is still very similar. Number three, half-life. This is the time it takes for half the isotope's reactivity to decay. And different isotopes decay at varying rates. So the half-life of a substance X is the time it takes for half of it to have decayed to something else and half of it to still be substance X over here. Number 4, they're dangerous. They're harmful, potential harm. Radioisotopes can be damaging to biological molecules, which means their use needs to be really carefully controlled. This is why, when we use them in medicine, I have to ensure I choose very carefully which patients to refer for something that uses isotopes, because they could be harmed if we're not careful. Radioactivity. Ecology and the environment. Let's look at that. So radioisotopes also help scientists track nutrient distribution. They can look at the waste impact on sea and land animals, and they can even understand the dispersion of pests everywhere. And by following radioisotopes in ecosystems, we can actually study long-term effects and monitor the changes in that ecosystem. You can even put carbon radioisotopes into feed and then track that from plant into the muscle tissue of an animal to see how it metabolizes its food into parts of itself. It's amazing. We can look at dating of sedimentary rock as well in geology. So radiometric dating uses the decay of isotopes to determine the age of specific rocks that we're studying. For example, potassium-40 decays down to argon-40 over time. And by measuring the amount of argon trapped in rocks, we can estimate the age of that rock. Now, that method is useful for dating rocks that are hundreds of thousands to millions of years old. That's how we know how all different layers of mountains are and how long it took for the mountain to form. Carbon-14 dating is another interesting one, especially for nutrition, actually. Very interesting for nutrition, in fact. Carbon-14 is continuously formed in the atmosphere through cosmic rays acting on nitrogen with a half-life of about 5,500 to 6,000 years. This isotope decays very slowly, turning into nitrogen-14. So we're measuring the carbon-14 content in samples. We can estimate the age of once living organisms, whether it's bones or wood or plant remains. The accuracy technique is very well documented as well. Isotopes in medicine are something quite close to my heart, as I'm sure you can imagine. Radiation, as we know, can kill cells, even cancer cells, but it also harms healthy tissue. This is where radioimmunotherapy steps in. It's a method designed to target cancer cells very specifically and not the rest of the body. In this process, an antibody that recognizes a specific antigen on cancer cells is chemically attached to a radioisotope. And once injected into the body, the radio-labeled antibody targets the cancer cells, delivering radiation directly to the tumor. Now, one such example here is the use of iodine-131. It's got a half-life of just over a week, 8 days, something like that. And it emits both beta and gamma radiation. And we've used it for decades in treating thyroid cancer. In fact, I'll get the decay of iodine-131 to, I think it's xenon-131 in a diagram on screen for you somewhere around me, if Rahul or Jimmy from Longwave Digital wouldn't mind obliging me. What's happening when we use it is that the emitted beta particles, which are just fast electrons, by the way, that's all, they travel only a short distance through the tissue. And so that localizes the damage to the tumor only, while gamma radiation that's also emitted and goes further allows us to image where it is. So it helps doctors target the affected area more accurately because we can track positioning by tracking gamma radiation being emitted. And that precision facilitates better diagnosis and better treatment if you're someone that urgently needs it. And we also have clinical isotope tests. These are when patients see their GP or general doctor. And it's another great example. In clinical medicine, isotopes can have diagnostic uses too. A carbon-13 breath test is used to detect Helicobacter pylori, which is a bacterium responsible for stomach ulcers. Carbon-13 is a stable isotope, not radioactive, and the test works by detecting the breakdown of urea into carbon dioxide. The carbon-13 labeled CO2 can then be detected in the patient's breath if the bacterium is present. That's why going this fundamental in science down to an atomic level allows me to work in areas like metabolism with great clarity and appreciation for why changes in the body happen. Isotopes in metabolism is therefore something I'm interested in too. They offer a very wide range of applications in research. Some common isotopes used are carbon-14, as I mentioned, iodine-131, as I mentioned, and even, say, phosphorus-32, among others. And these are attached to biomolecules like fats, carbohydrates, and proteins to allow us to trace various biochemical processes from the journey of what we're eating to what happens in our bodies when we digest them, or even if we digest them, depending on what we're studying. Overall, the potential uses of isotopes are endless. They can be applied to track metabolic pathways, analyze enzyme reactions, or even detect the presence of specific proteins in cells using radio-labeled antibodies. A technique called autoradiography helps detect the radioactivity by using a photographic film. It's like taking a picture of radiation, and that gives us visual proof of where the isotope is actually located. Scientists can even date ancient remains. They can trace chemicals and ecosystems. You can use isotopes in medicine to target cancer cells, like I said. They've become truly indispensable tools in both research and clinical medicine. And I hope you're starting to see why going all the way down to an atomic scale is the best way to start understanding how to read scientific papers, how drugs work, why certain foods engage certain metabolic pathways inside us, and so on and so forth. Now, for those that really want to learn, let's take what we've talked about even further in this lesson number 1 of what will be a very huge course ultimately. All the elements we've spoken of so far are presented in something I'm sure you've seen at some point before: the periodic table. The modern periodic table. The modern periodic table is grounded in atomic theory, exactly what you've just learned. The periodic table on screen now is very simple, yet very extensive in the data that it contains. Each element's individual box shows the chemical symbol, atomic mass, sum of protons and neutrons, and atomic number of protons. Elements are arranged in horizontal rows called periods, which go across, and columns called groups, which go down. This is labeled on the top left. Elements within the same group share similar chemical properties because they have the same number of valence electrons on the outside. For instance, group 1 elements are monovalent, forming only one bond, while group 13 elements are trivalent, able to form 3 bonds. Group 18 contains the inert or noble gases, which don't readily bond with any other element, really. The periodic law states the properties of chemical elements are a periodic function of atomic number of protons. And remember, atomic number can relate to the number of electrons as well on the outside because they equal the number of protons. And it's those electrons that do the handshaking with other atoms to form bonds and cause change. What about the valence in the octet rule? Well, atoms with complete outer or valence electron energy levels, like we've seen earlier, they are more stable, than those that don't have full outer orbitals. Sodium, Na, for example, has the electron configuration 1s2, 2s2, 2p6, 3s1, which you can see on screen now. Yes, I know that off by heart. By losing one electron, it loses an amount of negative charge. This means it now has one more positive proton in the nucleus than there are negative electrons in the energy levels. So the atom as a whole now is a net +1 in charge. That's why sodium forms the Na plus ion and attains a stable electron configuration of neon, 1s2, 2s2, 2p6. It's the 3s1 electron that's lost. Similarly, chlorine, Cl, gains an electron to achieve a stable configuration of argon, 1s2, 2s2, 2p6, 3s2, 3p6, forming Cl minus, because by gaining an electron, it has now one more electron than there are protons in the nucleus. Sodium being really happy to lose an electron and chlorine being really happy to gain one is why they love each other, and so easily can form sodium chloride, which breaks down in water to Na plus and Cl minus when they're mixed in. These properties are trends in the periodic table. Group 1 elements, like sodium, they require very little energy to lose one electron, while group 17 elements, like chlorine, have a strong tendency to gain an electron. So you see a lot of group 1 stuff easily making compounds with a lot of group 17 stuff. And as you go across a period from left to right, the outermost electrons become more tightly bound to the nucleus due to increasing nuclear charge, thanks to more protons in the nucleus as you go from left to right. Conversely, moving down a group, the outermost electrons are further from the nucleus and are more shielded from its attraction, from the positive protons trying to attract the negative electrons to keep them where they are and not be attracted by something else that's nearby that's possibly trying to steal them. These horizontal and vertical trends influence atomic radius, ionization energy, electron affinity, and electronegativity. And if you're willing to listen, I want to teach you what they are. Remember that there'll be a lot more teaching like this to help you improve your life in the school community. The course you're watching and future ones, of which many are planned, won't be fully on YouTube. Just a few videos from them, like this one. So, atomic radius. The atomic radius is defined as half the distance between the centers of two neighboring atoms. It decreases across a period from left to right due to increasing nuclear charge, which pulls electrons closer to the nucleus. Moving down a group, the radius increases because additional electron energy levels are added, like Russian dolls in between, that layer up on top of each other, making the outer electrons further from the nucleus. Ionization energy. Ionization energy is the energy required to remove an electron from an atom. The closer and more tightly bound an electron is to the nucleus, because the positive protons are attracting it in place, the more energy is required to remove it. The tighter something is chained up, the harder you need to pull in order for it to come off the chain. Ionization energy increases across a period as atomic radius decreases, and ionization energy decreases down a group. So electron affinity reflects the ability of an atom to accept an electron, like our chlorine example earlier. So elements with higher nuclear charge, such as group 17 halogens, have high electron affinity because the addition of an electron results in a completely filled outer shell. Hence why Cl minus chloride is made so easily in that sodium chloride example I gave. Electronegativity is a measure of how strongly an atom attracts electrons in a chemical bond. A bond is how two atoms are connected using electrons. It's how they're shaking hands. The higher the electronegativity, the greater the attraction for electrons taking part in that handshake. Electronegativity increases across a period from left to right, and it decreases as you go down a group. But what about biology and physiology? Well, about 25 of the 92 naturally occurring elements, which I mentioned at the start of this video, are essential to life. Carbon, oxygen, hydrogen, and nitrogen make up about 96% of all living matter. Then phosphorus, sulfur, calcium, potassium, etc., a couple of other elements, they account for the remaining 4% of an organism's weight, roughly. Biomolecules are constructed using carbon to form the framework, while hydrogen, nitrogen, oxygen provide functionality based on how many and in what way they connect to the carbon. Sulfur and phosphorus are important in biomolecules And trace elements like, say, iron and magnesium and zinc, they all play critical roles as catalytic components in enzymes. Once you understand why certain elements behave in certain ways, you then understand why certain molecules behave in certain ways. Then you understand why certain things happen in the body. You understand why glucose can glycate other molecules to cause damage. You understand why heavy metals are toxic if consumed. You understand why insulin is required for glucose to enter cells, but not fats. If you stick with me, I'll take you from subatomic particle structure all the way to living your life with the best possible hope of being disease-free and the longest lifespan possible, whilst looking as good as you can in every photo. This is just the first lesson in what will be an enormous course. And even though I want to give it away for free like I am now, the whole thing, as well as so much more stuff just like this, as well as live classroom teaching and treatments and consultations and case studies and scientific paper analysis and more, will be for the paid school group when it launches in January 2025, alongside the free one. I'll announce it here, as well as on my Instagram at dr.abs, doctor.abs, and my website in the description below when the time comes. I hope to see you there, and stay tuned for lesson number 2 in this course.